Hi, I'm Patrick Regan. Welcome to Advanced Networking Concepts Part 6, Network Virtualization Part 1. During the next two videos, we'll discuss technology used in modern environments that include network virtualization. In Part 1, we'll discuss SDN, SD-WAN, and NFV. As always, stick around for the practice question at the end to test your knowledge and help you prepare for the Network Plus exam. If you find this video helpful, don't forget to click the like button, and if you have not already, subscribe to the Pat Has Your Back channel for more tech training content and technical know-how. Network virtualization is the process of abstracting physical network resources, such as switches, routers, and firewalls, into software-based logical entities. This allows multiple independent virtual networks to operate simultaneously on a single shared physical infrastructure. Network virtualization creates a software overlay on top of the physical network fabric, which separates network services from the underlying hardware. A network hypervisor creates a logical representation of network nodes and links, managing resources like bandwidth and capacity independently of the physical devices. It consists of virtual components, which are software-defined versions of hardware, such as virtual switches, virtual routers, and virtual network interface cards, which handles traffic within this virtual environment. Network virtualization is often conceptually divided into or achieved through Network Functions Virtualization, or NFV, which operates at the OSI model layer 2 and 3, and Software Defined Networking, or SDN, which operates at the OSI model layer 4 through 7. While they're distinct technologies, they're frequently grouped together as the primary pillars for transforming physical networks into virtual software-based environments. The primary differences and roles are Network Functions Virtualization, or NFV, focuses on network services that replaces dedicated physical hardware like firewalls, load balancers, and routers with software that runs on standard, off-the-shelf servers, virtual machines, or containers. Software-defined networking, or SDN, focuses on the network architecture by separating the control plane, which decides where data goes, and the data plane, which actually moves the data. It allows for centralized, programmable management of the entire network through a single interface. Both NFV and SDN are complementary, but not dependent on each other. You can have SDN without NFV and vice versa, but they are most effective when they're used together to create a fully agile and automated virtual network. Network Functions Virtualization, or NFV, refers to the concept of running network functions like routers, firewalls, and load balancers as software-based virtual machines running on a hypervisor, which runs on standard hardware instead of dedicated physical appliances. Running as a virtual machine or appliance allows greater flexibility, scalability, and cost efficiency within an SD-WAN network. It essentially separates the network functions from the underlying hardware, enabling them to be deployed and managed independently. Key points about NFV and SD-WAN include virtual network functions. Individual network functions like routing, security, or WAN optimizations are implemented as software-based that run on virtual machines. Commodity hardware. Unlike traditional network devices, NFVs can run on generic x86 servers, reducing hardware cost. Centralized management. An NFV orchestrator manages the deployment, scaling, and lifecycle of NFVs across the SD-WAN network. Benefits of using NFV and SD-WAN include agility, which allows quickly add or remove network functions based on changing needs. Scalability, which allows easily scaled network capacity by adding more virtual machines. Cost efficiency, which utilizes standard hardware and avoid dedicated appliance cost. And flexibility, which allows to deploy different network functions based on specific site requirements. Software-defined networking, or SDN, which is the underlying technology that allows for centralized control and management of network infrastructure through software, essentially forming the foundation for optimizing WAN connectivity across geographically dispersed locations by applying SDN principles to a wider network area. It involves the use of Application Program Interface, or APIs, to control and manage network devices programmatically. SDN separates the control plane from the data plane, allowing administrators to manage network devices and their behavior through software applications using APIs. It provides flexibility, automation, and programmability in network management. Essentially, SD-WAN leverages the core concepts of SDN to manage and optimize a wide area network or WAN. Software-defined wide area network, or SD-WAN, is a technology that uses software-defined networking principles to manage and control wide area networks more efficiently. SD-WAN enables organizations to connect and manage multiple sites, such as branch offices, data centers, and cloud resources, by dynamically routing traffic across a mix of transport services like MPLS, broadband internet, and LTE. An SD-WAN can intelligently route traffic based on the application being used, can be set up with a minimal manual configuration, can utilize various underlying network connections like MPLS or broadband without restrictions, and is managed through a single central console where all network policies are defined and applied across the entire network. Remember, SDN is used to primarily manage local area networks within a data center or enterprise campus, focusing on centralized control of network traffic. SD-WAN applies SDN principles to connect multiple geographical dispersed locations over a WAN, optimizing data routing across different network types like MPLS, broadband, and LTE. SDN and SD-WAN give users the ability to tune or manipulate how the network behaves, creating virtually unlimited possibilities for enhanced performance and customization. Key features of SD-WAN include the following: intelligent traffic routing. SD-WAN uses application-aware routing, which directs traffic based on the performance needs of applications, such as prioritizing critical applications like VoIP or video conferencing. Centralized management. SD-WAN platforms provide centralized control, usually via a cloud-based dashboard, allowing administrators to easily monitor, configure, and manage the entire WAN from one place. Zero-touch provisioning. New network devices can be added to the SD-WAN network automatically with minimal manual configuration, simplifying deployment and reducing setup time. Improved security. Most SD-WAN solutions offer built-in security features such as encryption, firewalls, and intrusion detection, and integrate well with third-party security services. Policy-based management. Administrators can create policies to control how traffic flows across the network based on the type of applications, user, or site, improving both security and performance. And cost efficiency. The ability to use diverse, cost-effective internet connections while still maintaining application performance. SD-WAN creates an overlaid network that sits on top of existing WAN infrastructure. This allows you to manage traffic independently of the underlying network technology. SD-WAN continuously monitors network conditions and can automatically switch paths based on real-time performance metrics such as latency, jitter, and packet loss. SD-WAN provides direct internet access at branch locations, optimizing cloud application performance by reducing backhaul traffic through central data centers. In traditional WANs, traffic is typically backhauled through a central data center, which can increase latency for cloud-based applications and result in higher MPLS costs. SD-WAN, on the other hand, can route traffic directly to the internet or cloud service from the branch locations, improving application performance and reducing costs associated with backhauling. By moving to SD-WAN instead of relying on one best circuit, SD-WAN uses multiple transports at once. SD-WAN edge devices at sites build an overlay across these links, and the control applies consistent policy. As a result, SD-WAN brings centralized management, traffic steering, security, and application optimization. SD-WAN design is also used to connect branch sites and mobile users to the HQ, as well as directly to cloud, SaaS, and data centers. SD-WAN is more automated, whereas devices can be zero-touch, provided and configured via software, API-driven workflows. SD-WAN has become popular as it enables organizations to adapt more flexibility to cloud environments and multi-branch connectivity needs while reducing reliance on traditional, more expensive WAN solutions. Management layer provides a single point of control. Control layer enforces policies and manages routing. Data layer or forwarding layer carries out the actual data forwarding and enforces local policies at the edge. These three layers work together to create an SD-WAN network that is scalable, flexible, and policy-driven. SD-WAN uses the following application programming interface, or API. Northbound interface is the point where applications and management systems interact with the controller, essentially providing a higher-level view to manage network functions. Southbound interface refers to the communications point between a higher level network controller and lower level network devices like switches and routers, allowing the controller to send commands directly to manage the network. Essentially, southbound means communicating with the network hardware, and northbound means communicating with applications that use the network. Application layer, also known as management layer or orchestration layer, provides centralized configuration policy, management, monitoring, and analytics. The main components include the SD-WAN controller or orchestrator, often cloud-based, that enables centralized oversight across all network locations. It is responsible for defines network policies and pushes them to SD-WAN devices such as edge routers and branch devices. Monitors network performance and application analytics, providing visibility into traffic patterns, bandwidth usage, and potential issues. And integrates with APIs to allow third-party management tools or external cloud services. Control layer facilitates communications between the management layer and the data layer, responsible for routing decisions and enforcing policies. It includes the control components that may include virtual or physical controllers at the network's core, which receive instructions from the management layer and translates them into routing information. It's responsible for managing the control plane protocols, routing updates, and topology information. It executes application-aware routing and directs traffic flows based on defined policies, ensuring optimum path selections based on factors like latency, jitter, and packet loss. And it establishes and maintains secure communications between SD-WAN devices and routes based on policies set in the management layer. Data layer, or forwarding layer, is responsible for the actual forwarding of data packets across the network. It includes SD-WAN edge devices, routers, and other hardware or software forwarding elements at branch offices, data centers, or cloud locations. It's responsible for applying traffic policies and routes packets according to instructions received from the control layer, encapsulating and forwarding data through the secure tunnels, and dynamically adapts to the network changes or outages by rerouting traffic as needed, and enforcing quality of service or QoS and security measures such as encryption to ensure data integrity and prioritization. SD-WAN is often used for multi-branch connectivity. For organizations with many branch offices, SD-WAN offers an efficient and cost-effective way to maintain reliable connectivity between sites. Cloud-first enterprises, companies that rely heavily on cloud applications, benefits from SD-WAN's direct-to-cloud routing capabilities. And business continuity and failover. SD-WAN can automatically reroute traffic in case of link failure, ensuring high availability for critical applications. SD-WAN has become popular as it enables organizations to adapt more flexibility to cloud environments and multi-branch connectivity needs while reducing reliance on traditional, more expensive WAN solutions. Some well-known SD-WAN providers include Cisco, VMware, Fortinet, Palo Alto Networks, and Silver Peak. Question: which of the following topologies is designed to fully support applications hosted on-premises data centers, public or private clouds, and SaaS services? Answer: SD-WAN. Question: which of the following types of planes propagates routing information in an SD-WAN solution? Answer: control plane. Question: an IT manager needs to connect 10 sites in a mesh network. Each needs to be secure with reduced provisioning time. Which of the following technologies will best meet this requirement? Answer: SD-WAN. Question. A network administrator needs to implement routing capabilities in a hypervisor. Which of the following should the administrator most likely implement? Answer, NFV. Question. A company needs to virtualize a replica of its internal physical network without changing the logical topology in the way that devices behave and are managed. Which of the following technologies meets this requirement? Answer, NFV. Question. A network administrator wants to control new router deployments via the use of application programming interfaces or APIs. This would be an example of what? Answer, software-defined networking. For more information, visit these sites. In summary, network virtualization is the transformation of a network that was once hardware dependent into a network that is software based. It decouples the network services from the underlying physical infrastructure, enabling the creation of logical or virtual networks that are independent of the hardware. Network functions virtualization, or NFV, focuses on virtualizing individual network functions like routers and firewalls, allowing them to run on standard servers instead of dedicated hardware. Software-defined networking, or SDN, which is the underlying technology that allows for centralized control and management of network infrastructure through software, essentially forming the foundation for optimizing WAN connectivity across geographically dispersed locations by applying SDN principles to a wider network area. Software-defined wide area network, or SD-WAN, is a technology that uses software-defined networking, SDN principles, to manage and control wide area networks more efficiently. Thank you for watching this video. The next video will be Advanced Networking Concepts Part 7, Network Virtualization Part 2. If you like this video, click the like button. And if you have not already, subscribe to the Pat Has Your Back channel. Thank you.